Applications of differentiation, showing that a curve has no turning points or points of inflection. Verify that the following curve has no turning points or points of inflection, and also verify that the curve is decreasing for all values of x, where x is real. Okay, if it has no turning points, what does that mean? At the turning point, we know that dy dx, the slope function, would be equal to 0. So if it had no turning points, it means that dy dx could never be equal to 0. So dy dx is not equal to 0. What does it mean to say the curve is always increasing or decreasing? Well, if it's always decreasing, it means that the slope is always negative. Again, this relates to the first derivative. So if it's decreasing, it means dy dx must be less than 0 or negative. And lastly, the point of inflection. At the point of inflection, the second derivative of the curve would be equal to 0. So if it had no point of inflection, it means the second derivative of this curve could not be equal to 0. So now we have to differentiate the curve. We see that it's a quotient, so we use quotient rule. U is x plus 2 and v, the denominator, is 2x minus 3. The quotient rule says the derivative is v times the u dx, so that's 2x minus 3 by the derivative of x plus 2, which is 1, minus u times, which is the x plus 2, times the derivative of the v dx, that would be 2, all divided by v squared. And we might multiply out just to neaten the top. So we have 1 times 2x and 1 times negative 3, and negative 2 times x and negative 2 times 2. We wouldn't expand the denominator. It's okay to leave it as a square. And we see there's a cancellation here. And so we get negative 7 over 2x minus 3 to be squared. What we might recognize about this expression is that it could never be positive. It could never be equal to 0. It's always negative, because the denominator here could never be equal to 0 or a negative value. However, it must be pointed out the denominator does not exist if x had the value 3 over 2. So this proves two of the points, really. It proves that it has no turning points because dy dx could not be equal to 0, and it also proves that the curve is always decreasing for all values of x, because the second derivative is always negative. In the second part of the question, for the point of inflection, we're interested in the second derivative. So I'm going to write out dy dx here first in index form, just because it's easier then to differentiate it. So it's negative 7 times 2x minus 3 to the power of negative 2. So we'll use the chain rule to differentiate this. The derivative of the outside would be, we'd multiply the negative 7 by negative 2, getting positive 14, reduce the power by 1, so it becomes to the power of negative 3, and then multiply that by the derivative of the inside, which would be the derivative of 2x negative 3 is 2. We could neaten it a little bit, so this becomes, to write in a fraction form, it's 28, 2 14s, all over 2x minus 3 to the power of 3. And the point about this is that if there's no point of inflection, it means that this could never be equal to 0. And we see that that's true. That this is not equal to 0, couldn't be equal to 0. So we can therefore deduce that this curve has no point of inflection